Hello everyone, I'm Yi Zhang from the optimization firm. Today I'm going to talk about this topic, solving continuous and discrete nonlinear programs with the global solver Baron. This is a joint work with Professor Sahinides from Georgia Tech, and today I will present the new advances in the solver Baron in the last 1 decade, and also we will review some of the important features that our colleagues has developed in the past. At the very beginning, let's look at this standard formulation for a mixed integer nonlinear problem. So here the set J represent the set of indices of integer variables in this problem. And when the set J becomes empty, this problem is simplified to an NLP problem. And in this talk, we assume that the function fx and gx are differentiable, and then we can use the gradient informations in the algorithms. And there are so many factors that are affecting the complexity in solving NLP and MINLP problems. For example, the convexity information or the model size. And in the past, there has been so many NLP solvers that are designed for solving the NLP problems. And here we listed some of the NLP solvers. We colored the local solvers in green and the global solvers in red. And all these local solvers differentiate with each other by the different local models or the strategies that they use for global convergence. Some of them use sequential quadratic programming, some of them use interior point method, and some solvers like ConOpt and Natural integrated different methods together for solving NLPs. And the global solvers mainly benefit from the branch and bound framework, and some of them utilizes the convexity information for NLPs. And then in this page, we still listed some of the popular MINLP solvers, and mostly they benefit from the tricks that developed for the NLP problems. And the local solvers, local MINLP solvers utilize different methods. Some of them use decomposition strategies to decompose MINLP into a series of NLP and MILP subproblems to solve. And the global solvers implemented the reduction strategies, the cutting planes, and the Presolve methods differently. So that's why we still see different performances in the current global solvers for MINLP problems. In this talk, we mainly focus on the global solver Baron. The history of Baron goes back to 1990s, and the first generation of Baron focused on nonlinear relaxations and generated Factorable reformulations. And then the second generation of Baron involved polyhedral relaxations and improved the local search for better efficiency and robustness to solve MINLPs. And nowadays, for the third generation of Baron, we are considering the correlations between multiple variables, multiple constraints, or the other informations that are embedded inside of the model, and we involved different types of relaxations, for example, linear, nonlinear, or mixed integer linear relaxations. And we are also introducing novel Presolve and reduction techniques to improve the performance. And in this talk, we will talk about the new advances, for example, Presolve, Convexification, hybrid relaxations, domain reduction, and we are exploiting the variability of different subsolvers in Baron. And for each core component that are listed in the previous slide, we will evaluate the impact of each one component in the collections for MINLP and NLP. And here we collected over almost 4,000 problems that are, and we also released all these problems in our website. And these problems are collected from the open source benchmark libraries, for example, the MINLP library or the IBM library. And for the NLP problems, we collected the problems from Global Library and Princeton Library. And we also collected the root node continuous relaxation for MINLP benchmark library. So that's why we see more problems in the NLP collection. And now we are talking about Baron. So at the very beginning, Baron will pre-precise the model that the user feed us. And we will reduce all the redundancies in the model. We will tighten the bounds on variables. We will just look into the model to see if there are any special structure. Once the problem is eliminated to nothing, then we can terminate with the final solution. Otherwise, we will start solving the initial lower bounding and the upper bounding problems. So here we are talking about the standard formulation as a minimization problem. So the dual bound is provided by a lower bounding problem. And once the gap is closed, we can terminate. Otherwise, we will start branching. And at every child node, we will also perform node presolve, domain reduction. We will add more cutting points to the relaxations. We will use a lot of different type of relaxations to get a tighter bonds. Once any condition for the termination condition for the branch and bound is satisfied, Baron will terminate with the final solution. In the newest version of Baron, we also provide many interesting features for expert users. For example, the users can set up options as the same as the past, and also the users can set up branching priorities for each variable. All the variables with 0 priority will never be branched on, and the variables with higher priority will be most possibly to be selected to branch. And the user can also let Baron know which equation is convex, because Baron cannot enumerate all the convex equations, and people are identifying more and more convex or concave expressions day by day. And the third feature here is that the user can set up the relaxation-only equations, which means an equation that will only be used for constructing relaxations, and it will not be used for local search. So this is a very interesting feature that the people can find in our manual. Once the problem is obtained by Baron, Baron will generate factorable reformulations for the model. For example, this if function is a nested nonlinear function for 4 variables x, y, z, w, and we decompose it into 8 new introduced variables, and each one represents a primitive function between variables. For example, linear functions, exponentials, monomials, or bilinear products. And nowadays, we identified that by incorporating some of the introduced variables, we can get better formulations. For example, this w log w, we know that there are good convex properties that we can use. This is obtained by incorporating T2 and T3. And then Baron starts from pre-solving the problem. So in Baron, we classify the pre-solve method into 3 categories. The first category is called basic pre-solve, which mainly utilize the original constraints and original bounds on variables, and we only identify the direct redundancies from the original model. For example, empty rows, empty columns, or fixed variables. And the second category is called inferential pre-solve, which heavily depend on the theorems or KKT conditions or some other theorems that are developed in the literature. So here we need to derive some formulas from the original model. For example, we need to identify the dominance relationships between each paired variables, and we need to solve some sub-problems like we need to do probing to identify redundancies. So inferential pre-solve is a little bit more expensive than basic pre-solve. And the third category is called reformulation pre-solve, which is the most destructive pre-solve method in these 3 categories. So reformulation will mainly just ruin the original model structure. For example, we can reformulate MILP problem, mixed integer quadratic programming problem, to an mixed integer linear programming problem once some conditions are satisfied. And here we evaluate the impact of pre-solve by performing experiment in the 2 collections, MINLP collection and NLP collection. So here these tables provide a lot of details for our experiment results, and we need to analyze this deeply. So this table shows the comparison between the default version of Baron and Baron without pre-solve. And here we split the collection into 2 categories. One is called solved, another is called timed out. So timed out category means that both these 2 solvers fail to solve the problems within the time limit, which is 1 hour. And in the solved category, we further split it into several brackets, and each bracket is labeled as larger or equal to n second, which means in this bracket, at least one solver can solve this problem, but the slower solver costs at least n seconds to solve the problem. So basically it means larger or equal to 500 seconds collects harder problems than the previous brackets. And here we are seeing that the impact of Presolve is increasing as the problems becomes harder, and Presolve decreases almost 98% of the solution time. And in the time-out category, we evaluate the final gap because both the two solvers failed to solve this problem to global optimality. So we compare the gaps. Then we see that with Presolve, we can find more problems with better gaps. And then the next point is domain reduction. Normally, we classify the techniques in domain reduction to two categories. One is called feasibility-based, another is called optimality-based. So for example, in this figure, we have two nonlinear constraints. And using these two nonlinear constraints, we can derive the box bounds on the variables x and y. We call that feasible bounds because we used the feasibility restrictions on the constraint 1 and the constraint 2, and we do bound propagations to get these two box bounds. And for optimality-based, people normally generate the objective cut, which is obtained by adding the lower and upper bound on the objective and use that as a new inequality constraint for the original model. And by using this objective cut, we can derive tighter bounds as shown in the green color. We call that optimality-based bound. And nowadays, we involved optimality conditions like KKT conditions, and we also derive novel conditions for special structured MINLP problems. And use those kind of conditions, we can derive gradients, and then we can improve the bound propagation to get tighter bonds. And here we show the impact of domain reduction. And in these two tables, you will see that domain reduction brings almost a similar amount of improvement in these two libraries. And as we know, domain reduction is just a submodule of the Presolve, so that we see similar improvement compared with the impact from Presolve. And then the next core component is called Primal heuristic and local search. So for this part, we are introducing multiple different primal heuristics in the literature. For example, the feasibility pump, the neighborhood search. And the special thing here is that we developed special local search strategies for MINLPs. For example, we are performing progressive diving with rounding heuristics. We are also solving subproblems when necessary. And by doing this, we normally see better upper bound just at the root node. So that provides a very good starting point for the entire branch unbound. So here we evaluate the impact of local search, and you will see that the impact of local search is more obvious for the NLP library, and it only decreases 88% of the solution time for MINLP library. So this is because for NLP problems, once the problem is identified as convex, and then the local search can directly terminate the problem with global optimality claim. But for MINLP, local search has to provide a solution that can also satisfy the integrality conditions. So this is normally harder than NLP problems. And then we are talking about the dual bounding set. For the dual bounding problems, we need to involve a lot of tight supporting hyperplanes, cutting planes to make the relaxations tighter. And now we know that there are so many convex expressions identified in the literature, so we are continuously improving Baron by introducing more and more convex expressions, including something like second-order cone, and also the convex equation functions that are listed in the right-hand side. And also we are generating convex and concave envelopes for different types of functions. And the most interesting point today is about how to utilize the correlations between variables and constraints. For example, some binary variables can be identified as indicator variables when they are involved in a constraint with continuous variables. And then we can generate tighter cutting points based on those kind of informations. So here the two tables for convexification show us that convexification can reduce the number of timeout examples. You can see this number more clearly from the MINLP results. Originally, without convexification, Barron times out for over 3,000 problems, almost half of the library. But with this convexification, many bounds can be closed before the time limit, and then we see only 33 problems that are timeout in this bracket. Then the next point is about hybrid relaxations. So just now we mentioned that we use convexification techniques to involve more and more cutting points. With the increase of the cutting points, the size of the relaxation will increase, and the normal LP relaxations may be harder to solve. And sometimes the MILP relaxation, it provides tighter bonds, even though it consumes more time. And in Barron, we are introducing quadratic programming relaxations and also convex QCP relaxations to get tighter bonds in sacrifice of the solution time. So here we show the impact of relaxation. Similarly, we see that the impact of relaxation is higher on the MINLP library, because for NLP problems, once they are identified as convex, they can be terminated at the root node without solving any lower bounding problem. So that's why we see the impact of relaxation is higher on MINLP library. So as we said, Barron needs to solve different types of relaxations and subproblems. And there we rely on the subsolvers, for example, LP subsolvers and NLP subsolvers, to solve these relaxations. But interestingly, we find that almost 16% of the NLP solutions from the subsolvers are not reliable. Sometimes they return us with a local optimal solution, but in fact, they violate the KKT conditions. So we need to be very careful in filtering these solutions. Otherwise, Barron will terminate with wrong optimality claims. And also for LP solvers, we find almost 1% of the final solutions from the LP solvers are incorrect. And then we perform the comparisons between the local solvers and global solvers in the collected models. So here we perform the experiments in the same environment with the same global optimality tolerance and feasibility tolerance. And also we use 1 hour as the time limit. And we perform all the experiments under the GAMS platform, because GAMS has an examiner that can evaluate or examine the feasibility or optimality of our final solution. First, we classify the models into 4 categories. So the first one is called trivial. So we identify problems as trivial when they are solved within 1 second by all solvers. And we classify one model into timeout category when it cannot be solved by any solver within the time limit. And once any solver claims there are missing bounds in the model, we classify that model into the final missing bounds category. And for all the other remaining models, we label them as solved. So we compared all these solvers in these solved models. First, we compare the performance for the NLP collections, and here we provided a simplified version from the Barron solver. So once the user set up the option fees local to 1, Barron will directly terminate when the first local solution is found. Then we call Barron lock is a local solver. And here we also compare all these local solvers with the virtual best solver that does not exist in the real world, but it just extract the best solution time from all the compared solvers. Then we know how the other solvers behave compared with the virtual best solver. And in this collection, we identified that over 2,000 problems can be identified as convex by Barron. So here in this table, we can see that natural and IP-opt follows closely to Barron lock. And compared with the virtual best solver, you will notice that virtual best solver is ahead of all the other solvers by almost 400 problems. That means all these solvers have their own drawbacks too, and they have their own space to improve. And here we know that Barron utilizes different local solvers eternally, but here we further limit Barron lock to use only one local solver, and then we can get a clearer comparison results. For example, we only allow Barron to use ConOpt as its local solver. Then we compare Barron lock plus ConOpt with the standalone ConOpt, similar for the other solvers. Then we can see Barron lock is ahead of ConOpt minus SNOPT with the help of its own reduction techniques, but there are some a little bit overhead in the Barron lock compared with IP-opt-H and Nitro. So once the reduction techniques in Barron lock is embedded inside of the IP-opt or Nitro or the other local solvers, we are expecting the local solvers to behave more efficient and to solve more problems. And then in this page, we compared all the global solvers for the NLP library. Here we separate the entire collection and the problems that cannot be identified as convex. So in this table, we see that all the other global solvers are almost over 2 times slower than Barron. In this page, we show the performance profiles for all these compared global solvers on the NLP collections. And here you will see for the problems that are easy to be solved, Barron can be already very fast at the very beginning. And the very beginning, Barron can solve over 30% of the problems. So in this page, we compared all the global solvers on the MINLP benchmark library. This library collects about more than 1,000 problems. And here we see Barron still leads the role, but we see that Barron and Scape solves almost the same number of problems. And the virtual best solver is ahead of all the other global solvers by solving over more than 100 problems. So that means there are still space for all the other global solvers to improve, to catch up. And in this page, we compared all the global solvers in a larger set of MINLP problems. And here we see that Barron has the shortest shifted geometric means in the solution time. And here we also show the one-to-one comparisons between Barron and all the other global solvers. And here we can obviously see that each local solver has their own benefits, and we need to carefully analyze the data structures of each model and to improve the core components with specific targets. Finally, our conclusions are presented here. The first point is that we presented new features in the recent versions of Barron, and each core component makes Barron about 1 to 7.5 times faster on the collection of NLP and MINLPs. And the reduction and relaxation techniques are the most important factors, and people need to be very careful on these two parts. And compared with all the other local and global solvers, we see that Barron lock is obviously faster than the other local solvers because we use Presolve, we use reduction. And also, compared with other global solvers, Barron is at least 2 times faster on the NLP problems and 1 to 4 times faster on the MINLP problems. But all the solvers fall short behind the virtual best solver. So this is a very important information because we always realize that there is so much space for us to improve. So our future work includes some policies like to wisely select relaxation variance and different subsolvers, and we are also exploiting the correlations between variables, and we are looking into special model structures to improve our reformulation techniques and all the other reduction techniques. So these are all the interesting points for today's talk. I hope these are helpful for you, and thanks for listening.